How does a language model know that the word king is closer in meaning to queen than it is to bicycle? How does a search engine find documents that match your question even when they share no words in common? The answer is embeddings. In this episode, we go line by line through what embeddings are, how they are generated, and how to use them in Python. Machines cannot process raw text. Everything going into a neural network must be a number. The naive solution is to assign each word an integer ID. Cat gets 1, dog gets 2, king gets 3. But this is useless. These numbers carry no meaning. Mathematically, cat at 1 is closer to dog at 2 than it is to king at 3. But semantically, cat and dog are both animals and are far more related to each other. We need a smarter system, one where the numbers themselves encode meaning. An embedding is a list of floating point numbers that encodes the meaning of a piece of text. In this simplified example, each word is represented by just 4 numbers. Look at cat and dog. Their numbers are very similar. Look at king and queen, also very similar. Now, compare cat to king, completely different. The position in this numerical space captures semantic meaning. Words that mean similar things end up with similar numbers. In practice, real embedding models produce lists of hundreds or thousands of dimensions, capturing much richer relationships. Generating embeddings in Python takes just a few lines. We import the OpenAI client, which automatically reads your key from the environment. We call the embeddings create method, passing the model name and the input text. The model text embedding 3 small is fast, cheap, and great for learning. The response gives us a list of 1,536 floating point numbers. We never need to understand what each individual number means. What matters is that similar text will produce similar list of numbers. To compare two embeddings, we use cosine similarity. The formula measures the angle between 2 vectors in high-dimensional space. If 2 vectors point in the same direction, the score is 1, meaning identical. If they point in completely different directions, the score is near 0. Here, the 2 Python sentences score 0.93, extremely similar even though they share almost no words. The sentence about the stock market scores only 0.21 against either of them. The math is doing exactly what our intuition would do. Now, let us build a real semantic search engine. We start with a small list of documents. The key insight is that we embed all documents exactly once and store the resulting vectors. This is important. We never re-embed documents on every search. We pay the cost one time, and from that point on, searching is just maths. In the next scene, we add the actual search function. The search function embeds the incoming query, then scores it against every stored document using cosine similarity. We sort by score and return the top results. The query is, what city is the Eiffel Tower in? The system correctly ranks the Eiffel Tower document first and Paris as the capital second, even though the query does not contain the words Paris or France. This is semantic search. It finds meaning, not just matching keywords. And this is the core idea that all of RAG is built on. 3 mistakes catch almost every beginner. First, never compare embeddings from different models. OpenAI and Cohere embeddings live in completely different vector spaces. The scores will be meaningless. Second, never re-embed your documents on every query. Embed once, store the vectors and reuse them. Third, do not embed extremely long text as a single chunk. Embeddings compress everything into one vector, so long documents lose specific detail. We cover chunking strategies properly in episode 3. You now know what embeddings are, lists of numbers that encode meaning. You know how to generate them, how to measure similarity with cosine distance, and how to build a basic semantic search. In the next episode, we cover vector databases, how to store millions of embeddings and search them in milliseconds, instead of looping through a Python list.